Have you ever wondered what happens to the water we use after it goes down the drain? Whether it's from our sinks, toilets, factories, or streets, that dirty water doesn't just disappear. It enters a complex system designed to clean it before it can safely return to the environment or be reused. This is where wastewater treatment comes in. Wastewater treatment is not just about removing dirt. It's a vital process that protects health, preserve ecosystem, and ensure we don't run out of clean water. Today, we'll explore how this process works. From the moment wastewater enters a treatment facility, through physical and biological filtration, all the way to the safe release or reuse. So, what is pretreatment? Pretreatment is the first stage of wastewater treatment process. It removes large debris and grit to protect downstream equipment and improve the efficiency of subsequent treatment steps. Now, let's talk about the objectives of pretreatment, and I'll give you a few examples to help you picture it better. First, pretreatment prevents clogging and abrasions in pumps and pipes. For example, if someone flushes plastic wrappers or sanitary pads, this can get stuck and damage the system. By using screens and filters, we remove those before they cause problems. Second, it protects the biological and chemical treatment process. Let's say there's cooking oil or harsh chemical in the water. This can harm the bacteria used in biological treatment. Pretreatment helps by removing oils using grease traps and harmful chemicals using neutralizers. Third, it reduces wear and tear on chemical components. Think of small rocks or sand in the water. Over time, this can grind down the metal parts like pumps and mixers. Using grit chambers early in the process remove these abrasive materials. And finally, pretreatment improves efficiency and reduces maintenance costs. For instance, if we remove solid waste early, we won't have to stop the system, often for repairs or cleaning. That means smoother operation and lower expenses. Let's go over the main steps in the pre-treatment process. The first step is screening. This removes the large floating solids such as plastics, rugs, sticks, and paper that could clog or damage the equipment. Screens used can be bar screens, which catch larger, coarser materials, and fine screens, which capture smaller particles. These screens can be cleaned manually or mechanically depending on the facility setup. The second step is grit removal. These steps targets heavier inorganic particles like sand, gravel, and small stones. A grit chamber is used here where the water slows down just enough to let the grit settle at the bottom. This protects pumps and the other equipment from the abrasions. Third step, grease and oil removal, or also called degreasing. These steps removes oil, fats, and grease which could interfere with aeration or clog the pipes. Facilities use degreasers or skimming tanks. These let grease float to the surface which it is then skimmed off. The fourth and last step, and also optional but important in larger systems, is flow equalization. Helps balance inflow rates, especially during heavy rainfall or industrial discharge. It stores excess wastewater temporarily and then release it gradually into the treatment units, preventing overload and making the treatment process more stable and efficient. These steps make sure the wastewater entering the main treatment process is as manageable and clean as possible. So guys, now you can see on the screen the equipments that are commonly used. So first, trash racks. Second, mechanical and manual bar screens. You can also see aerated or vortex grit chambers, grit traps or scum baffles, and lastly, flow equalization basins. Now, let's go to the primary treatment. Now, let's dive into the next stage, which is primary treatment. After pre-treatment takes out the big and bulky stuff, primary treatment steps in to deal with the finer and suspended solids. Think of it like this. If pre-treatment is like combining out leaves from a swimming pool, primary treatment is like letting the finer dirt settle at the bottom or flow to the top so we can skim it off. This is done using physical processes like sedimentation or edge skimming. So, why is it important? There are three big reasons. First, it removes suspended solids and lowers the organic load, making it easier for the next stages to do their job. Second, it boosts the efficiency of secondary treatment. We're basically setting it up for the success. And third, it helps protect the biological systems downstream from being overwhelmed or damaged by the sudden heavy loads, also known as shock loading. In short, primary treatment clears the way, literally and figuratively, for the rest of the treatment process. Let's take a closer look at the key stages of primary treatment. First is sedimentation. In this step, wastewater flows into the large tanks called primary clarifiers or settling tanks. Here, heavier solid settles at the bottom and form what we call primary sludge. At the same time, lighter materials like oils, fats, grease flow to the surface and skim off as a scum. The second one is sludge collection and removal. The sludge that settles at the bottom doesn't just stay. It's scrapped and pumped into the sludge digester or holding tanks. Later on, this sludge can be treated for reuse, like being turned into fertilizer, or it may be safely disposed of. And the third one and last is scum removal. Meanwhile, the scum, which includes oils and grease, is skimmed off the surface and collected separately. This is important because it prevents clogging and protects the biological process in the next treatment stage. Let's discuss the significance of primary treatment within the entire wastewater treatment process. First, it reduces the load on biological or secondary treatment. By removing a large amount of suspended solids and floating water early on, primary treatment ensures that the secondary stage, which involves microorganisms, isn't overwhelmed. Second, it makes the entire process more cost efficient. With fewer solids entering the next stages, less energy, equipment use, and chemical are needed. This saves both time and money for the treatment facilities. Third, it minimizes chemical and energy use in downstream processes. The cleaner the water before entering secondary or tertiary treatment, the fewer chemicals and less energy are needed to achieve clean water standards. And lastly, primary treatment prepares wastewater for effective secondary treatment. It acts like a first filter. If this step is done well, it sets off the biological stages for success, leading to a better treatment results overall. In short, primary treatment doesn't just clean the water, it makes the entire system work more smoothly and sustainably. So now guys, you can see on your screen the equipments commonly used for primary treatment. You can see primary clarifiers, scraper mechanism for sludge pumps, and surface skimmers for scum.
Secondary treatment is where biology takes center stage. This is where microorganisms get to work, breaking down dissolved organic matter that we can't see but is still harmful. So the main thing we're targeting here is BOD, or biochemical oxygen demand. This is a key indicator of how polluted the water is. Basically, the more organic waste in the water, the more bacteria needs oxygen to break it down. And when bacteria use too much oxygen, that then that's bad news for fish and other aquatic life because they need oxygen too. Like to visualize, think about pouring milk into a river. Then bacteria will start breaking it down, right? But in doing so, they consume a ton of oxygen, creating what's called an oxygen demand. And that's why we need to remove as much BOD as possible before the water gets released. Secondary treatment is categorized into types based on how microbes are used. First is suspended growth systems, where bacteria are freely floating in the water, kind of like ingredients in a soup. And second is attached growth systems, where bacteria grow on surfaces like moss and rocks. So let's look in on the most widely used suspended growth process, the activated sludge process. In the activated sludge process, wastewater is pumped into a large tank called an aeration tank. Here, we introduce air or pure oxygen to create the ideal environment for aerobic bacteria to thrive. These bacteria feed on the organic material in the water and form flocks or clumps of microbes that stick together. These flocks act like tiny little cleaning crews, munching through the pollutants. And after enough time in the aeration tank, the mixture flows into a secondary clarifier. This is a settling tank where gravity does the rest and flux settle into the bottom of the container as a sludge, hence the name activated sludge. From here, we do two key things. We return some of the settled sludge back into the aeration tank to keep the bacteria population going, and this is called return activated sludge or RAS. And then the excess sludge, which keeps building up, is removed as waste activated sludge or WAS to prevent overgrowth and system imbalance. So if you watch how sourdough starters work. It's basically the same concept here, where you keep a portion to continue fermenting the next batch and discard the rest. Now that we've talked about how the activated sludge process works, let's zoom in on its key features and what it actually achieves. First is efficiency. The activated sludge process is capable of removing 85 to 95% of organic pollutants when properly managed. That includes a significant drop in BOD and suspended solids. Second is flexibility. It can be adapted based on the treatment goals. Like, for example, with slight modifications, we can also include nitrogen and phosphorus removal within the same biological setup, making it a bridge to tertiary treatment. And third, sludge recycling. This process includes continuous recirculation of a portion of the microorganisms. Remember that RAS or return activated sludge that we mentioned, that makes the system self-sustaining and biologically stable. Fourth is settling and clarification. After aeration, the separation of flocculated biomass in the secondary clarifier is crucial. Good settling results in a clear effluent and a dense sludge, while poor settling, often called bulking, can lead to a carryover and poor water quality. So, to sum it up, activated sludge is not just bubbling tanks like you see in the picture. It's a carefully balanced biological ecosystem designed for high efficiency treatment. Now let's explore another biological approach, but this time with a different setup, which is attached growth systems. And it has two common examples: trickling filters and rotating biological contractors or RBCs. In trickling filters, wastewater is sprayed over a bed of rocks or plastic media. A slimy microbial biofilm then lives on the surface. As the water trickles down, the bacteria digest the pollutants, and it's a bit like water filtering through a mossy garden. And in RBCs, on the other hand, use large rotating discs partially submerged in wastewater. As they slowly turn, the biofilm alternates between exposure to air and wastewater, promoting healthy bacterial growth and efficient pollutant breakdown. So let's take a closer look at the trickling filters. Despite the name, these aren't really filters in the traditional sense. They're more like bioreactors. The setup usually involves a large circular tank filled with media, often rocks or gravel or specially designed plastic. Wastewater is then sprayed or distributed over the top using a rotating arm or fixed nozzles. As the water trickles down through the media, it passes over the biofilm, as the slimy layer that I said earlier of microorganisms that clings to the surface. These microbes digest organic pollutants as the water flows past. And trickling filters are also low maintenance, energy efficient, and naturally ventilated, which makes them great for small to medium sized treatment plants. However, their performance can vary with temperature and they require a larger land footprint compared to compact systems like the activated sludge. Now, on to rotating biological contractors or RBCs, another common attached growth system. In RBCs, you have a series of large flat circular discs mounted on a rotating shaft, as you can see in the picture. These disks are partially submerged in a throw of wastewater, and as the shaft slowly turns, each disk is in becomes in and out of the water. And then microorganisms grow on the surfaces of these disks and form a biofilm, just like in trickling filters. But what's unique here is the alternating exposure to air and wastewater. This creates ideal conditions for aerobic bacteria to thrive and break down organic material. RBCs are modular, quiet, and energy efficient, making them a great choice for smaller communities or decentralized treatment systems. And one added benefit is because the disk rotates slowly and continuously, there's less risk of clogging and maintenance is relatively straightforward. By the end of secondary treatment, we've typically removed around 85 to 95% of the organic material, but we're not quite done. And then we ask why not? Because there are still nutrients like nitrogen and phosphorus that can trigger the algal blooms, and also pathogens like viruses and bacteria that might still be present. And depending on the wastewater source, micropollutants like pharmaceuticals, hormones, or metals might remain in the wastewater. This is where tertiary or advanced treatment comes in. Tertiary treatment is essentially the final polish, while primary and secondary treatment get the water safe enough for environmental discharge. Tertiary treatment, on the other hand, takes things further, purifying water to the point where it can be safely reused, or even for drinking in some cases. We remove nutrients like nitrogen and phosphorus, pathogens including bacteria, viruses, and protozoa, and even trace pollutants like medicines, pesticides, or heavy metals that I mentioned earlier. This stage is especially important for water reuse in agriculture, industry, or potable applications. Also take note of this. There are four treatment methods: filtration, nutrient removal, disinfection, and advanced oxidation processes or AOPs. First is nutrient removal, which becomes essential when we're discharging into sensitive ecosystems or aiming for high quality reuse. So why does it matter? When excess nutrients like nitrogen and phosphorus remain in the treated water, they can lead to eutrophication. That is a process that fuels algal blooms and robs water bodies of oxygen. That results in fish kills, foul odors, and serious ecological disruption. Plus, legal discharge limits for these nutrients are getting stricter around the world. So let's break it down. Nitrogen, nitrogen removal. This happens in two main biological steps. First is the nitrific First is the nitrification under aerobic conditions. Bacteria convert ammonia into nitrite and then into nitrate. And denitrification. In anoxic or low oxygen conditions, another set of bacteria convert that nitrate into nitrogen gas, which simply escapes in the atmosphere. Together, these two processes remove nitrogen effectively from the water without needing chemicals. And in phosphorus removal, there are two main methods: chemical precipitation and enhanced biological phosphorus removal. So essentially, we're using either chemicals or carefully selecting bacteria to pull phosphorus out of the water. And both methods have their place depending on the treatment goals. Now that most of the organic matter is gone, we move on into filtration, a crucial step that removes the fine particles left after the secondary treatment. The purpose here is twofold. First, to enhance water clarity, and second, to prepare the water for disinfection. The clearer the water, the more effective downstream processes like UV or chlorination that I will explain that later will be. There are two main types of filtration that we use: granular media filtration and membrane filtration. In granular, this includes traditional setups like sand filters or dual media filters, where water flows through layers of sand or gravel or anthracite, which trap fine particles by physically straining and a bit of adsorption. And in the membrane filtration, this takes it up a notch. Here we use physical barriers with very small pore sizes, like microfiltration or MF can remove suspended solids and some bacteria, or ultrafiltration or UF, which goes further. It can remove smaller particles and even many pathogens like viruses and protozoa, where in both cases, this is purely physical process and no chemicals, just a tight barrier that screens out what's left. And it's especially important for reducing the turbidity, which is a key factor in water quality and safety. So, in short, filtration isn't just about making the water look cleaner, it sets the stage for the final critical step, disinfection. Disinfection is the last essential step to ensure that the water is safe from disease causing organisms before it's released or used. The goal here is to inactivate any remaining pathogens like bacteria, viruses, and protozoa that might have slipped through the earlier stages. So let's go over the three main disinfection methods. First is the chlorination. This is the most traditional and widely used method. Chlorine is added to the water, and while it's highly effective at killing microbes, it can also lead to the formation of disinfection byproducts, which can be harmful in large quantities. So, managing dosage and contact time is crucial. And then the second one is the ultraviolet or UV light. This UV light disrupts the DNA of microorganisms, preventing them from reproducing. It's a chemical-free option, which makes it attractive for many treatment plants. However, UV systems need very low turbidity, so filtration beforehand is essential for maximum effectiveness. And third is the ozonation. Ozone is one of the strongest oxidizing agents used in water treatment. It's excellent at destroying pathogens and also helps with the odor and taste control, but it requires more energy and specialized equipment to generate and apply it, which makes it more expensive than the other two. Each method comes with trade-offs in terms of cost, safety, and effectiveness, and the best choice often depends on the specific goals again of the treatment facility, whether that's discharge, irrigation, or portable reuse. So lastly, this is just an additional. After this infection, there's still one more advanced stage in some treatment plants, especially those focused on water use or tackling emerging pollutants, and that is the advanced oxidation processes or AOPs. The goal of AOPs is to remove trace contaminants that are not typically caught by standard treatment methods. These include the pharmaceuticals, pesticides, and um, endocrine disrupting compounds that I mentioned earlier, substances which can still pose environmental and health risks even in small amounts. So how do they work? AOPs generate hydroxyl radicals, written as OH, and these are extremely reactive and non-selective oxidants. That means they aggressively break down complex organic molecules, reducing them into harmless or simpler substances like water and carbon dioxide. There are also several ways to generate these radicals. Some common combinations include UV and hydrogen peroxide, or oxygen and hydrogen peroxide, or UV and ozone. So the benefit of this is that APOs are able to destroy persistent pollutants without leaving behind harmful byproducts. It's a clean, powerful approach, especially useful for water polishing before sensitive discharge or portable reuse. In short, AOPs represent the cutting edge of water treatment where we go beyond just clean and aim for truly pure and safe water.
Now, let us move on to sludge handling and management, where in this topic we will dive into its handling and management, which includes collection, treatment, and disposal. First of all, what is sludge? Sludge, or also known as biosolids, is a byproduct of wastewater treatment, and it is composed of organic substances, of which includes insoluble and adsorbed soluble impurities that turn into residues during treatment. Sludges usually contain priority chemicals and heavy metals, which makes them highly toxic and is regarded as a hazardous waste. To add to this, there are a few types of sludges, such as sewage sludge, which comes from settling tanks, and industrial sludge, which comes from industrial wastewater treatment plants. Now, why does sludge need to be treated and managed? As mentioned earlier, sludge contains chemicals and heavy metals, which is a hazardous type of waste, and proper disposal and management is required. Untreated sludge has a negative effect on the environment and public health. It can cause diseases and pollution to its surroundings. Now, what does this mean? This means that there is a growing concern and demand for treating sludges and its proper disposal. In recent studies, the Philippines is said to produce approximately 375 bone-dry metric tons of sludge daily from wastewater treatment plants. And with the growing population, we can expect it to rise to 600 plus metric tons per day by the year 2040, making it unnecessary to find alternative methods in treating sludge waste. Now, how do we even handle and manage sludge? A report by Malenab 2019 studied that the prioritization of treatment types in the Philippines. They mainly mentioned 4 types of treatment and management for sludge. Those are mainly being composting, anaerobic digestion, incineration, and alkaline stabilization. First, composting. Composting is an aerobic process which aims to sanitize wastewater sludge through eliminating toxic compounds and microorganisms by using primary or supporting procedures such as adding bulking agents like wood chips, sawdust, sunflower stalks, and corn cobs, which help them stabilize the sludge, which is then incubated without aeration for at least 21 days. This will result in a decrease in odor as well as pathogenic organisms. Although with many benefits, there is one major flaw in this process, and that is the production of greenhouse gases such as methane and other volatile organic compounds. Next up, anaerobic digestion. Anaerobic digestion treats wastewater sludge by turning the organic matter into biogas, more specifically methane, and significantly reducing the amount of solid waste in sludge as well as reducing pathogenic microorganisms. Its process involves breaking down organic matter through hydrolysis, acidogenesis, acetogenesis, and methanogenesis. In simple terms, anaerobic digestion breaks down the organic matter without the presence of oxygen and produces biogas as a product. However, anaerobic digestion plants still need to be optimized and further study techniques is recommended. Next up, incineration. Incineration or air disposal is regarded as one of the most successful treatments to wastewater. It treats the sludge by oxidizing organic matter at high temperatures and producing ash as a byproduct. However, recent studies have stated that this method has no longer considered the best viable option since it produces large amounts of carbon dioxide which contributes to air pollution. Next up, alkaline stabilization. Alkaline stabilization is performed to reduce pathogenic microorganisms, reduce odor, and promote environmental protection. Alkaline stabilization uses chemical reagents to produce high pH conditions with the process of hydrolysis, weak acid-base chemistry, precipitation, and solid-liquid separation to eliminate the pathogenic microorganisms. In addition, there are few more ways to handle and manage sludge, and those are landfilling and dewatering. Landfilling is the most common way of disposing waste. In this method, a substance called leachate, a special wastewater, is produced due to the high concentration of pollutants present in landfilling. And around 1 ton of leachate is equivalent to 100 tons of urban household wastewater. Furthermore, the treatment of and disposal of wastewater products produces high concentrations of ammoniacal nitrogen, which causes eutrophication of water bodies. Next up, dewatering. A process called sludge dewatering is used to remove the moisture and reduces the volume of wastewater sludge, thereby minimizing its transport costs and downstream sludge management. Now, to sum things up, every method of sludge handling and management has its own advantages and disadvantages. However, by using a criteria such as environmental factors and economical factors, it was determined that the composite treatment is the most viable option, followed by the alkaline stabilization, anaerobic digestion, and incineration. However, the best way to solve these disadvantages is to target the source directly, and that is done by minimizing wastewater entirely. Now, wastewater minimization for sustainability. After discussing wastewater treatment, let's now discuss how we can minimize wastewater. The term wastewater minimization refers to the method that reduces wastewater produced by the urban sector, industrial sector, and even the commercial sector. This method aims for the prevention or the minimization of sludge and rather than treating the sludge produced. And therefore, by aiming for less wastewater production, it is more sustainable in the long run. In addition to this, aiming for wastewater minimization, we can achieve the following SDG goals. SDG 6 for clean water and sanitation, SDG 12 responsible consumption and production, and SDG 13 climate action. Now, why is this important? First of all, it conserves water resources. Since water is a scarce resource and fresh water is only about 3% out of more than 70% of Earth's total water. By minimizing wastewater, we allow more efficient water reuse techniques. Hence, it also reduces treatment costs because there is less wastewater to treat. Furthermore, we discussed earlier the disadvantages of different sludge handling and management methods. They have one thing in common, and that is their yield of pollutants, which affects the environment and even the human health. By reducing wastewater, we significantly reduce the amount of pollutants released into the environment, and therefore providing a more sustainable solution for the environment. In addition to this, regulations such as the Philippine Clean Water Act of 2004 or the Republic Act 9275 is implemented to show the importance of clean water resources. How do we exactly minimize wastewater? Companies such as PepsiCo and its Philippine counterpart, PepsiCola Products Philippines, have started to practice responsible water management by following the 3 Rs: reduce, reuse, and recycle. To manage water consumption, they also reported that they are working with government sectors like Laguna Lake Development Authority to assess and protect waterways in the communities they operate in. Another company is San Miguel Corporation, which implemented a program called Water for All, which aims to cut non-product utility water by around 50% by 2025. They also mentioned that they established water-saving measures and set water consumption levels. Now, these are only two among many companies that show their initiative in promoting a healthier environment and a goal for a more sustainable future. These actions demonstrate how all of us bear a responsibility for our environment. Each one of us plays a big role in minimizing wastewater and in climate action. By learning proper habits such as conserving water, proper waste disposal, and adapting eco-friendly practices, we can contribute to a better and more sustainable future. Change begins with us.